Hello, students. In this video, we wrap up the content for Module 6 entitled Beyond Linearity. And we had those three topics to cover: smoothing splines, local regression, and generalized additive models. So let's begin. Smoothing splines. So smoothing splines have essentially the same objective as regression splines. So imagine we still have a response variable y that depends on or that we view as depending on a predictor x, um, but via a function that is not necessarily linear. And so we want to estimate this function. Here we're going to call it generically g of x. That is hopefully a good approximation of y. Now this g is not necessarily linear, but we still want it to be reasonably smooth. And so one way to achieve this, we saw it already, was the regression splines. But here we have a new idea, a new way to obtain such a smooth function g, and it's the smoothing spline. So what we're trying to achieve here is this. Let's review. Again, generically, this function that we want to approximate or fit the x such that g of x is close to y, we call it generically g. So we still wanted to minimize the mean squared error, meaning we want any observed value y to be close to g of x. But in addition, we want the function g to be smooth, and this is why in the minimization problem, we not only minimize the mean squared error, but we minimize it with the so-called penalty, this term here. Because imagine this term wasn't there, and here g doesn't need to be linear, of course. So then if g is free to be whatever, you could have a function that is extremely variable, like wobbly, if you will, that essentially interpolates all the points and has a perfect fit on your training data. Meaning you choose a function such that g of x is always exactly equal to y. That's going to be an extremely wobbly function, but then you will achieve that this term, the mean squared error, will be exactly zero. But it's not good, of course, to do that because, as we've seen many times, this is overfitting. Your function is way too flexible. You'll have a mean squared error of zero on your training set, but your predictive power on a test set will be bad. So what we add is this penalty, which again is a penalty to enforce smoothness of the function g in the minimization problem. So again, yes, this is a penalty on the roughness of g. So by roughness, we mean the opposite of smoothness, meaning that if g is very rough, so not smooth and wobbly, well, this term will be big, and hence, well, it's going to be bad in the minimization problem. Meaning that, again, because you want to minimize this, if this is too large, you're not going to minimize it. So you're going to force the function to be reasonably smooth to minimize the whole thing. And here lambda is a parameter, so you can pick it to be bigger or smaller. The bigger the lambda, it means we penalize more having a rough fit. So yeah, if you really want your fit to be smooth, you can pick a bigger lambda because then the penalty for roughness will be large. Now let's explain why. Why is this integral a penalty for roughness? So I'm saying that if this is large, it means your function is very rough, very wobbly. Well, yes, because this is simply the second derivative of the initial function g. And yes, this is a measure of wobbliness of the function because recall, well, the first derivative of a function is the rate of change of the function itself at a given point x. Okay. Otherwise said, it's the slope of the line that is tangent to the function at that specific point x. So if you have say a parabola, well then, yeah, the slope of the line that is tangent to the parabola at any point, that's your first derivative. Now the second derivative is the rate of change of that slope of the tangent line. So you see, if the second derivative is large in absolute value, equivalently, if the square of the second derivative is large, it means that the slope of the function keeps changing. Otherwise said, the function is very, very wobbly because again, the slope keeps being uh, positive, negative, positive, negative because the function is very wobbly. It's not like a nice, smooth increasing function or decreasing or maybe increasing and then slowly it gets decreasing. That would be a smooth function because again, the second derivative doesn't keep, it's not large, right? So otherwise, the rate of change of the first derivative is small for a smooth function. Okay, hopefully that makes a bit of sense. And then what we have, okay, well, you can think of the two extreme cases here. If lambda is 0, well, there's no penalty for roughness, which means that the function that's going to minimize this thing will be very, very wobbly. As I said, you just interpolate all the training data points. So this is very flexible. You're going to have a training MSE of 0. But here, what you do is you train bias for more variance, and you're not necessarily, you certainly not have the best fit. And then, well, the other extreme case is, of course, if the penalty for roughness is infinite, well, then you're going to force the function g to be the smoothest it can be. And the smoothest function you can have is a straight line. Well, yes, because a straight line has a first derivative that is a constant, and hence the second derivative is 0. So if lambda is infinity, well, the only way this thing will be small is if the second derivative is exactly 0, and this happens only if g is a straight line. Now, the problem to if g is extremely flexible, if g can be anything you like, the problem to minimize this is not an easy problem. And here we don't spend any time on showing this. We give it to you, the sort of final result, that the g that minimizes this thing turns out to be what you could call a shrunken natural cubic spline. So remember, a cubic spline is a piecewise polynomial of order 3 that is forced to have first and second derivative continuous. Now it's shrunken here because we constrain it to be smooth via this penalty here. But so the solution is then this natural cubic spline, and recall natural means that outside the boundaries of our data, the cubic spline is actually a straight line. So if you recall, maybe we can show you the picture from, yeah. So the natural cubic spline is forcing at the extremities here the fitted curve to be a straight line, but only at the edges, at the extremities of your data set. Okay, so again, the solution is a natural cubic spline, but careful with knots at every single training data point. So recall that for a spline, you need to pick knots. So you need to pick the breakpoints at which the equations change, the fitted parameters of the cubic spline change. But here we're saying the knots are actually every single data point, x data point. Now, as a comment, I said smoothing spline, regression spline, they achieve the same sort of objective. And in fact, for your information, for mortality smoothing, so smoothing the mortality rates in mortality tables, apparently the US-based mortality tables use smoothing splines, and UK-based mortality tables use regression splines, which is a bit interesting to see that, okay, both approaches are actually used to achieve similar objectives. Why do you need to smooth mortality rates? Well, mortality rates can be non-smooth, the raw mortality rate. Well, yes, because thankfully dying is a pretty rare event. So in a given population, especially for young ages, there's not that many people who die. So the raw mortality rate before any smoothing can be quite rough from age to age. Anyway, this is more for your information. Now, okay, a bit of illustrations for this. Yeah, so in R, you can easily obtain smoothing splines with simply this function smooth spline, which pretty sure doesn't require any package. It's in base R. Now, just careful with the syntax that you need to feed before, well, as first argument, the x, the predictor, and as second argument, the response. So now in our example from before, again, mortality example, so the age is the predictor, of course, and then the log of the mortality is our response. And you can give it a certain, this is the effective degree of freedom. We're going to say a few words about this effective degree of freedom after, but in your mind for now, just know that there's a link between this lambda and the effective degree of freedom. But again, I'm going to explain this in a second. For now, okay, a smoothing spline with 2 degrees of freedom is a straight line simply because here you can view the degrees of freedom, only 2 here, as simply 2 parameters, so the slope and the intercept. So you only have 2 degrees of freedom, so you can only fit a straight line, slope and intercept. Okay, as we said before, this is a bad fit for this data. But now if you increase the number of degrees of freedom, for example, degrees of freedom 4 here, well, now the fit looks way, way better. It follows the data, or the trend in the data at least, pretty closely. If you keep increasing, you increase the flexibility of your model in terms of a lambda here would be a smaller lambda, so a smaller penalty for roughness or wobbliness. If you do that, you're going to get a fit that is more wobbly. So you see, let's go to the extreme. If the degrees of freedom are large, you're allowed to fit the data, I suppose, more closely, but it creates a function that is less and less smooth, more and more wobbly. Now, choosing this lambda. So yeah, I think as we explained already, if lambda is small, you are more flexible, but rougher fit. So you have the danger of overfitting. Now, this effective degrees of freedom that we denote here, df lambda, depends on the lambda. If if lambda is small, we are more flexible, so the number of degrees of freedom is higher. So yeah, high df means small lambda and means more flexibility for our smoothing spline. And the actual technical definition of this effective degree of freedom, that doesn't need to be an integer, because so it's not really a number of free parameters as what usually means or is intended by degree of freedom. So it's more complex than that. And here we don't present all the technical details for this, but it's the same idea, right? The more degrees of freedom, the more parameters are free to vary in the model. But just bear in mind, it's not exactly a number of parameters. It doesn't need to be an integer. But you can simply choose the lambda that is the best for your data by cross-validation, meaning you try different lambdas, and for each of them you compute the cross-validated mean squared error of your fit, and that's a good criteria to pick the lambda. And it's not the only criteria you can use, but it's a reasonable one. And in particular, you can again, we don't present the mathematical details, but it turns out that the leave one out cross-validation, mean squared error, is computationally simple to compute. There's a shortcut formula that allows you to compute it like one shot. You don't need to compute it n times as you would expect with leave one out cross-validation. Because remember, leave one out cross-validation means that you split your data into n different folds. Well, every fold has only one observation, that is the one you use to compute the test mean squared error. But anyway, here the point is just that leave one out cross-validation is available in a computationally efficient way, and I'm just going to show you in a second that R does this for you if you tell it. And just a comment here that because we said here the solution is a natural cubic spline with knots at every data points with smoothing splines, I suppose an advantage is that there's no arbitrary choice for the knots. So, well, because we have a cubic spline, there's also no choice of the degree. So that's nice in the sense that you don't have this choice to make. And also, you don't need to choose the location of the knot. So it's essentially here, your life is kind of simple because you only have one thing to choose. It's the degrees of freedom, but which again, you can just rely on cross-validation to choose. Yeah, in regression splines that we covered before, you need to choose the order of the polynomial. I mean, often we use degree tree, but still, technically you need to choose it. And you also need to choose the number of knots and the location of the knots. Okay, so in R here, for our Luxembourg mortality data, you can do the fit easily. So this is what we had before. But here just I'm picking cross-validation to be true. So in this function smooth splines, if I say cross-validation equals true, it means R will pick the lambda or equivalently the number of degrees of freedom that minimize the cross-validated mean squared error. So that's nice. Here, for your information, we get the number 5.08, which I suppose could makes some sense here. It does look like if the degrees of freedom is too high, the function is kind of too wobbly. But if when it was like, okay, I don't have 5 unfortunately here, but if it was 4 or 6, yeah, the fit looked, at least to the naked eye, good and also very smooth. And here just for plotting the data with the fitted spline, it's very easy. 2D scatter plot of your data points, you can just use the function lines, and R picks up smartly, I suppose, that lines to which you give your fitted model will automatically plot the line of prediction, the line of best fit. By best fit here, I simply mean that the model that was here chosen by cross-validation. And here, just an example from the textbook. Again, it's the example we've seen many times, wage as function of age. You have two lines of best fit. Both of them are smoothing splines, but one, for some reason, they've chosen 16 degrees of freedom. That's a red line, and you see, well, it's not bad, but it is a little bit wobbly, right? It seems to go up and down, which probably there's not a good reason here for it to go up and down that much, as opposed to the line with 6.8 degrees of freedom. Looks like a random number, but it's the one that is chosen by leave one out cross-validation, and this is the blue line, and it's less wobbly, it's more smooth, but both are pretty similar. Okay, now the next topic is local regression. Local regression, same objective. We want to fit some y via some predictor, but via possibly a nonlinear function. So frankly, the objective is similar to regression spline, sorry, or smoothing splines, but it's a different approach. Now, what's the idea? Predict the response. Here we're going to call it y0 to mean a data point that is new, associated with predictor x0. Now, careful here, via a linear fit, but only using the data points in the training set xi, yi that are close to x0. So if you want to approximate what the y should be for given x, you will do this with a linear fit, but local at x. So let's explain that with the procedure to do that, like here called the algorithm. So first step is that you're gonna gather only the fraction of the points that are close to your x0, and this is characterized here by this s. Now, s is k over n, where k is simply the number of points, that are the closest to n. So here, I think I'm making this more complicated than it is. Let's say that your s is 20%. Well, you're just going to pick the 20% of points that are the closest to your x0. So this is a fraction of the total number of points. Total number of points being n, of course. Now, so here there is an arbitrary choice, which is s. So you would need to pick, okay, s, I pick it arbitrarily to be 20% or 30%. A little bit like in a smoothing spline, you arbitrarily pick lambda. So here in this case, the arbitrary choice is about the proportion of points you consider to be close to x0. So again, you would say, for example, okay, I'm going to pick the 20% of points that are the closest to my x0. And closest in their x values, of course. Okay, closest in their x values. Okay, second step, for all of these points that are deemed to be close to x0, each of them, you give them a weight, now here generically called k. So this is the weight you give to a point xi that is close to x0, but now this weight is based on the actual distance to x0. So a point that is extremely close to x0 would have a higher weight than a point that is further. Now, points that are outside those k nearest neighbors, because again, remember here we pick the k points that are closest to x0, those points that are further away, they have a weight of 0. And then what we do a least square regression like usual, simply that now we have a weight on every point that is inside our linear regression. So we minimize this quantity. What is this quantity? Imagine that there was no weight here. This would just be the line of best fit on the whole data set. But now we simply say, okay, we do a line of best fit, but observations that are very close to our X have a bigger weight in the in the fit. And remember here, I mean, we're summing up to n, but remember that the points that are not in the neighborhood, they get a weight of 0. And so again, conceptually, maybe I can show you the picture here. Conceptually, if you are at a point here denoted by the orange line, say a point of around x equals 0.05, we're saying, okay, we're going to fit a line, meaning the line that describes how well, that predicts y as a function of x. We're going to use only the points that in x are close to this x0, and in this case, those are the orange points. More than that, we give a weight to those points in the fitting that is higher if a point is very close to x0. So for example, this point here has a bigger weight than this point here, because this point here is further away from x0. And that's it. The last step is simply that now, because you've done your line of best fit, well, local line of best fit, now you can predict y0. Because again, that's always the final objective. We want to predict the y as function of this x. And now the y is simply a linear function. But again, a linear function that is locally fitted. Of course, beta hat 0, beta 1, 0 would be the solutions here when you minimize this quantity. Okay, so again, that's the illustration. Maybe let's look at the picture on the right. Here we're saying, okay, if our x0 is around here, around 0.45, what we do is we consider only the points that are in this interval, the points that are orange, because we picked a S that I don't know what S here is. I don't think it's written there, but looks like we're picking maybe 1/3 of the points. Okay, so maybe S is like 32% or something like that. And again, we just fit our line, but we fit it locally. So the line we fit for that specific point x0 is 0.45 is represented there. Now overall in this picture, we also see the entire line of best fit. So basically all the y hat 0 fitted using this method, but again, the point here would have been obtained from a local fit at this exact point. And you see the result is a smooth function because as you move, you're moving the k nearest neighbors just a little bit. So your fit is going to change just a little bit when you go from x0 to x0 plus a small quantity and so on. So overall, you get a line that is a line that is smooth, relatively smooth, and obviously not linear, which is nice. I don't think I have too many more things to say about this this line. Oh, I think the blue line would be the theoretical true one, which you see here. It seems to be working pretty well. Fitted line is close to the real line. By real, I know it's the real one only because this data is generated synthetically with the computer. Okay, just a few comments about local regression. Okay, as we said, it's a weighted regression, and you only use the points that are close to a given x0 to fit the y at this specific x0. So you don't obtain a global equation of best fit. You cannot write that this function here is a certain function of a few parameters. No, because at every point you do a different fitting. And so maybe a disadvantage is that you do need to run this procedure for every single x0 point at which you want a fitted y0. And so here, by the way, yeah, this orange line appears to be smooth and continuous. I suppose it was fitted for maybe, I have no idea, right? But 100, 200, 500 data points or something like that. And then R has drawn a nice smooth function among all those, say, 500 fitted y0 to x0. Used for updating models to recently obtained data. Well, yes. If you get just a few new data points that are in a specific range for x, well then you don't need to refit your orange curve to completely. You can just refit it for where those new x's are. Um, then as a comment, it's possible to extend this idea to a few predictors, maybe two or three, maybe four if you're lucky. Um, but by predictors, I mean simply if let's say you have two x, so one would be x1, x2 in two dimensions, then you can do a local fit where you use x1 and x2, where again, like now x point would be in two dimensions, and you would find all the nearest neighbors around this two-dimensional x. So conceptually, you can do exactly the same. Find the the nearest neighbors, and then again, in this example of two predictors, you would fit a plane. So a linear regression, but with two predictors would be a plane locally. There's a bit of a problem with that is that you can do that in many, many dimensions because of I think some people call this the curse of dimensionality. Conceptually, it might make sense in any dimension, but in reality, what happens when you have too many dimensions is that you'll have very few, if any, training observations in the neighborhood of most points. Uh, yeah, just because as the number of dimensions increases, it gets very, very unlikely that that 2 points will be close in every single dimension. Um, yeah, uh, because in one dimension, let's say that your S is 10%. Well, you'll have 10% of the points that are going to be close to the specific x0 in that dimension. But if you add another dimension, then only 10% of 10% will be close to that point. So only 1% will be close. And so this gets a very, very small proportion very quickly. Okay, and then lastly, okay, same data set, but now instead of using smoothing splines or regression splines, um, we use local regression. And again, if um, if your span, so this S is smaller, it means that your fit is more local, which means you have more freedom for your fit to be, well, to be flexible, I suppose. So you have more degrees of freedom here. So that would be the red line. But again, you are more rough. You are more wobbly in your fit. Here, if you use a bigger span, in this case 0.7 apparently, you have less freedom, but then the fit will be more smooth. And here it looks to be doing a better job overall, the blue curve. Okay. And then last topic is the generalized additive models, also called GAMs. This is where we put everything together and we can then fit a multivariate model, meaning that you explain y via several predictors. And all of those predictors, you can potentially transform them to have nonlinear relationship between each of these predictors and the y. So what we're saying is this. Yeah, we can transform several predictors in a nonlinear way and put them all together in one model to predict y, as exactly as we did in linear regression. And so just conceptually what we do is this. We simply say, okay, our response is now a function of, okay, an intercept, but then some nonlinear function of the first predictor. So here, xi means observation I, but then first predictor. Okay, xi1, first predictor. xi2, second predictor. Xi blah, 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 up to xip. Okay, so imagine that if you didn't have the f, or if f was just a constant times xi, well, you would have just standard multiple linear regression. But now we're saying those f can be whatever. You can call them the basis function that we saw before. And so in essence, we're simply saying, okay, if it looks like y is not a linear function of x1, but maybe it's a polynomial is doing a good job here. So if you transform x via polynomial, this would be represented by this f1 function, where f1 could simply be some constants times x, or x1, plus another constant times x1 squared. That would be a polynomial of order 2. Well, you can do that, but you can also then add another predictor that, again, you transform via some function f2 to make it a whatever you like, a regression spline, or a smoothing splines, or a step function, or maybe some of the x's are actually okay to keep as just themselves. So then you will have that y is a linear function of, for example, x2, but then x3 you want to transform it. So here essentially we're saying individually you can transform your x's, and then you put everything together in your global model for y as a function of those x's. Okay, so again, fj can be virtually any function of the predictors, but all those discussed earlier, again, polynomials, step functions, regression, smoothing splines, there are common choices. Um, okay, so again, you can find a separate fj for each predictor and then just add them together in your model. Obviously, you would ideally do all those diagnostics on your final model to make sure that even if this predictor once transformed was good to predict y, and this one was good to predict y. Once you put them all together, you still have that they're all significant, basically, because as we said many times, individually the predictors might be significant, but when you add them together, it might change their significance in your final model or multivariate model. Okay, we preserve additive property of individual effects. Well, so yes, here it's not fancy in the sense that we just have additive effects, which is still a limitation, I suppose. And there's no problem here to have a categorical response. Well, yes, if we had a classification problem where y is binary 0, 1, you could have the same idea. So you could have, yeah, your function of all the predictors could be this thing. But now if you have logistic regression, for example, um, well, recall, you just in logistic regression, you just have that the log odds uh, are this function. So yes, you would have the same. You would have the log odds of y equals 1 would be this now nonlinear functions of the predictors. Okay, just illustrations from the book. A GAM on which data where we've used for individual predictors again, we've used regression splines. Okay, and so we get the following fit for F1 as function of the year. Same thing, F2. Sorry, F2 would be uh, F2 is the as in the notation from the previous slide, right? It's the function of the second predictor. Here the second predictor is age, so F2 represents the effect of age on the response here, which is still wage, right? So as somebody ages, initially their wage increases, but eventually it kind of plateaus and then it goes down as they get older. So, and that's a good thing with GAMS. Interpretation is still easy. You can interpret the individual effect of individual predictors as you would in a model with only one predictor, right? So, um, all the other predictors held constant, you still have that. Okay, as age increases like that, the wage initially increases and then decreases. And if you have a categorical predictor here, level of education, I don't remember the exact categories, but high school, maybe undergraduate degree, postgraduate, or things like that. Well, you can still have this, of course, in your model, but here there's not really a transformation. Now it's just it's just that different levels have different average effects as you would have in standard linear regression. And yeah, and you get a similar, I think here, yeah, very similar thing if you do the same, but now instead of using regression splines to transform the numerical predictors, you use smoothing splines. Okay, you get something extremely similar in that case. Okay, a few comments. Yeah, obviously the big pro is that now you can have a multivariate model with nonlinear relationships between the predictors and the response. So hopefully giving you a better fit. And as I said, you can still interpret the effect of individual predictors on the response. However, model additivity potentially ignores interaction effects. It's true, although you can potentially solve that by adding the interaction effects in your model kind of manually, as you did in standard linear regression. So yeah, one could always add two-dimensional functions, any two-dimensional functions, right? So this function here is, again, very generic. You could have some more complex function of two predictors at a time. It could be an interaction effect, just x1 times, xj times xk, but it could be essentially anything you like, but of course it makes the modeling more complex. Okay, and lastly, a bit of our example now. So it's an example, but I suppose it's a little bit of not a warning, but uh, there's at least two packages that allow you to use or to implement GAMs. And frankly, here I don't have a recommendation on which one to use. In the book, they use the GAM package, so it's literally called just GAM. There's another one here called MGCV. So here we just present the results. So MGCV. Oh yeah, and what's a bit confusing is that okay, the package called GAM has a function called GAM that allows you to do this multivariate nonlinear fitting. But then this package, this is a package, like a library, uh, also has a function called GAM. So just careful about that. Here we're loading this library, and then within this library, we're going to use the GAM function. Now what we do then is, at least the syntax is simple. This is our Luxembourg mortality data, so the log of the mortality. We want to explain it by S. Okay, S is for smoothing splines. Okay, so we're going to use a smoothing spline on age and a smoothing spline on year. Now, we don't specify any parameters. If you wanted, you could specify here the degrees of freedom. So you could have age, comma, 4 for 4 degrees of freedom, or 5, or whatever. Now here we haven't done it, so we let R choose the best based on some internal criteria, the best degree of smoothing. Okay, so but be mindful that if you wanted to specify yourself the degrees of freedom, you could in this S function. And now we get the results. So simply plotting the model, select one means the first plot. The plot for the first predictor here, age. So you see more or less what we expected. Yeah, as a function of age, the mortality or log mortality goes down at first. Then here it kind of picks up that there's a bit of an increase in mortality around age 20, and then constant increase for older ages. The effective year looks very simple and pretty much linear. As the year go by, mortality decrease. But again, you could do that with the other library, which is GAM. So again, the library is GAM, and now the function that you fit is also called GAM. But careful that those are two different GAM functions. One from the library GAM, and the other one was from the library MGCV. And here, the syntax, I believe, is the same. Okay, here, okay, just for the sake of illustration, we do something slightly different. Instead of keeping year as a numerical variable, in which case it makes sense to fit a spline to it, we transform year to be a factor. This, frankly, I don't think is the right thing to do in this specific case, but it's just for illustration that you can put a factor, meaning a variable with just categories in your GAM, and the result will be quite different then. Okay, the first plot still illustrates the average effect of age on the mortality. Interestingly, here the fit is quite different. Is more smooth, but it's less precise. So here, again, we've used a smoothing spline to which we could have specified the degree of freedom, but now here we haven't. So R finds a way to optimize for the smoothness, and you get, for some reason, you get a smoother fit. So apparently, those two GAM functions, if you don't specify the degrees of freedom, can yield different fits. But lastly, what I would just want to point out is that because we've transformed the year to be a factor, there's no smoothing here because you leave that every single year will have a different coefficients for it. So it's going to be a step function. So yeah, at every year here, we have a different effect for the mortality. But of course, overall, it's the same trend. Like as years increase, the mortality decreases, which makes sense, but you don't get the nice smooth function you had before. Okay, here there's a bit of slightly funny descriptions of different curves that I let you review for yourself if you want. And again, okay, this is just a glossary. And here there's some extra videos about splines if you want to go beyond what we've covered, and another video about, I believe, local regression. But again, this is all extra stuff that I'll let you to review. For now, I'll stop here. Obviously, if you have any questions, you'll send them my way on the discussion board. as usual, thank you so much for your attention today.